So the talk I'm going to do today is Lambda called HardCore. Before I start with the talk, something about me. I'm Ratajski. I am just developer, coder, wizard, and an architect. So I'm mostly doing things with Java, JVM. It means also Scala and things like that. What I do for a living is, necromancy, I would call. So keeping things moving that should be dead long time ago, like WebSphere, Java EE, and things like that. Okay, and I live. You should see the picture. It's like the city under the mountain, among the dwarfs, and there was even a dragon long time before. So like I work for CSS Insurances in Switzerland. Great city, great company. Now about the talk. The most important warning for you. Lambda. If you expected that you at this talk learn something more about Java Lambdas or things like that, you would be disappointed. This talk is completely useless. For if you want to use it professionally, it's not for that. It's something funny, something a little bit scientific, but probably useless at your regular job. So if you are staying here to find some out hacks with lambdas, no, that's not a good room. Even though I think you can enjoy it. So we'll talk about things like what is a number. Momently make it bigger. We'll talk about Lambda Calculus, and we'll talk about this in Java. Okay, so, one thing, I am not a scientist. I am just a regular coder or wizard, whatever. Not a scientist, but I've studied mathematics. Why? I can explain, like in 90s, I was able to do that with my computer. It was Commodore 64. Who had Commodore 64? Yeah, great, it's a great machine, yeah? Atari is not good at all. I hope you know that. And yeah, so I had a colleague that was able to do this with his PC, and we've both understood at the moment while we are choosing our studies, there is nothing more sensible in computer science that we can learn. Yeah, because as we know, these tricks, it basically covers everything. So we decided to study something really challenging. It was mathematics, and the first lecture we had, really the first day, was that. The professor came to the stage and he was explaining, and he was making a mathematical proof that 1 is different from 0. So who is convinced that 1 is different than 0? Not that many people. Okay, so you should probably find out this proof. By the way, it was for me instantly, I realized, oh, that's great, that's really funny place. And for the first time in my life, after seeing this proof, I started to doubt about this. So I'm not sure if the professor really made a good job. Anyhow, so because the problem is, what is a number? So maybe, what is a number? Who knows what is a number? Who can explain me what is a number? What is a number?
Well, there are two definitions for numbers. There's a recursive function definition and the set theory definition.
Oh, great. So this guy knows everything. But who knows that also? Just raise your hand. Okay, so I will tell you. So because, everybody, numbers are for us obvious. We all learned them, I don't know, like we are kids, 3-4 years old. And then we see something like a 2, just number 2, like I have 2 things, and that's the number. But okay, to show you that, to visualize, I need some things like apples, whatever. And that's the problem, because surely numbers are not apples, surely are not electronic device. Number is something more abstract. And let's pretend this didn't happen. This picture should visualize Big Bang, so how the universe has started. Yeah, that's one of the theories. There is another quite popular that it was created by the flying spaghetti monster. But just for this talk, let's pretend nothing like this happened. The universe hasn't been created. It doesn't exist. Can we create in this empty, in this void, a number of something? What do we need to introduce the concept of the number? And as it was said, there is some way to do that by set. Of course, first of all, before we introduce numbers, we need to tell what is set. Set is just an abstract term, something. You probably all know what is set, but we don't define a set. But if there is a, that's just abstract term, little bit, I would say, easier to define, to describe than a number. Let's pretend there are sets. And right now we try to, with these sets, we try to do something with in this empty universe, not really created universe. What kind of sets can we introduce there? There is no universe. Can we have something there? Of course, we cannot have a set of apples. What can we have there? Have idea. What kind of set can we create? Can we describe in a not really created universe? That's easy. Empty sets. Yeah, exactly. So we can reason about empty set. Of course, that's easy thing, but it's not really pushing us far. So we have an empty set. Okay. What can we do with an empty set? So we have, right now in this universe, we have something. We have an empty set. That's one element. And set is something that we make of elements. So we can be very, very smart. We can create a set that contains this empty set. So we made a step forward. Yeah, like this. And I will not have time to really describe this procedure, but with this procedure we can go as far as we want. Just we take thing we had before and create another set bigger with that. So if you look at these three definitions, so the first thing that we have, it's something that we can call 0. The second, this set containing empty set is 1. This sentence there is something how we create a next thing in a sequence. So the set theory is like something successor for elements, and you see how, for instance, looks number 2 and number 3. So it was the set theory. How can we introduce numbers with something simpler, sets? And it was very, very consistent and elegant theory at the beginning. So mathematicians have created some few axioms, they are so called, and out of these axioms they could create things like numbers, all real numbers, natural numbers, all of them, and even whole mathematics. That's more or less that is a mainstream theory. That whole mainstream mathematics is built on top. It works even today. Why there were these mathematicians, it's like 200 years ago and 100 years ago, were doing that? There was one idea behind. Because if we describe the building blocks of the maths very, very well, consistent, maybe there would be a way to achieve something that was a holy grail of that time. That we can take any sentence, like any theorem, and we can just, using these building blocks, evaluate if it's true or false, like every theorem, like Pythagoras, whatever, because we have building blocks, so maybe, yeah, we just, out of these building blocks can produce this and, yeah, decide if it's correct theorem, valid statement or not. That was what was pushing forward these mathematicians to do this whole theory consistent and sensible, yeah? Why they were doing that? And then problems happened. Very consistent theory, like 6, 7 axioms that are very, very elegant, intuitive, even for kids. And then came a guy and asked these questions. Let's consider a set that of all sets that are no members of the set. That sounds crazy, but I don't have time to introduce, but it's like if you think about it, does the Is R a member of R? If it is, if we just assume it is, then looking at this, the sentence above, we see, yeah, but then it's not a member, so it cannot be. If we say it's not, then by definition it should be. So we have some kind of paradox. This paradox is called Russell paradox. And yeah, so set theory led to some paradoxes. And the problem was, what can mathematicians do? And they found a way, more axioms. It was exactly like every time you build a system, at the beginning you gather, and you, okay, this time we do it clean. That's our architecture. It's perfect, it's clean. And it works like that a month or two, and then comes a customer and said, and I need, by the way, this something working real time. And then you say, oh, it doesn't fit to architecture. What can I do? A hack. So in this moment, mathematicians, in order to fight with those paradoxes, and there were more, introduced hacks. It means the set theory is like 6, 7 elegant, intuitive axioms, and then 6, 7 completely crazy one that you wouldn't really understand. You have to spend a month to understand what those guys are talking about. It's not elegant anymore. So, yeah, what can we do with that? There was a guy called Alonzo Church. Who knows Alonzo Church? Not, of course, he is not living anymore, but you've heard about him. So, yeah, he had another idea. Maybe set is not a good start point. It sounds okay, but maybe it's not. Let's do something else, a function. So who knows what the function is? Nah. Okay, so if you are in school, you learn that function is something that takes elements from one set and transform to another. And you see instantly that's stupid, because in order to have a functions, you need a sets. That would be stupid. That's not solution. But okay, in Alonzo Church theory, functions work on functions and produce functions. We don't talk about sets anymore. Just forget about sets. We have only functions. Right now, we are in the same problem as before. World, universe wasn't created. So of course we could create there an empty set and all the numbers. We've shown it. What can we do with a function? Does there exist there a function in an empty universe, not created universe? Can you imagine, describe one function that it's easy to introduce, that's easy to create, that is easy to discuss? Empty function. What does empty function? Nothing. Yeah. That's so. What exactly?
The event exists.
Okay, that's you know much. You would I probably would need your help later, but okay. Right now, so identity function. What is an identity function? It's a function that takes something and returns exactly the same. So in the world, we have no universe, but we can describe this function. Okay, so its identity. By the way, mathematicians write it like that. It's a lambda taking x and returning x, like this. So if it takes this presenter device, it will return the same. You see? If it takes a mouse, it will return a mouse. It's very stupid, simple function. By the way, if it takes itself, so identity function, if it takes as an argument identity function, it will produce identity function. So as you see, we have empty universe, and we can already play with functions. Of course, at the moment, it's a little bit stupid, but it works. Okay, so, by the way, lambda, so who had played with lambda in any languages, computer languages? Oh, who had played with them in Java? Great. So, and this is how to play with them in mathematical words. So it's like lambda is just a symbol. After that, we put an x, that's an argument. By the way, there can be only one. So we have a functions of only one argument. And after the dot, we put an expressions. What will be result? So identity is simple, like result is x. Then we can describe two functions which are not really valid, but I will just visualize them to you. Like lambda from x produces x plus x. Okay? That's sensible lambda, like make it double, or sinus from x. The problem is we have an empty universe, and such operations as plus or sinus do not exist. We don't have them. No, we have to describe them first. We have to construct them. But, okay, so what can we really do? The only thing we can do in this universe is playing with lambda is to introduce new lambdas, and inside of the body of lambdas we have generally one possibility. Create a new lambda, or in an expression apply another lambda to some argument. So like this thing here means that having a lambda from x and f and x, by the way f and x are another functions, lambdas, and applying it to y, we get at the result this thing f, but in place of x we have y. And by the way, that's our language for today, for this speech. We only create lambdas that inside of the body of the expression have function applications and definitions of other lambdas, nothing really more. Sounds very, very constraining, but I will show you it's not a problem. So let's do it in Java, because probably this language with lambdas is not really, for you, very easy to follow right now. That's the way mathematicians, keep care about their jobs. Nobody understands their code, but we can make it easy with Java. So we'll create interface that's called lambda. Who knows how this interface can look like? Interface for lambdas. Okay, I will start. Functional interface. Oh, not this. Sorry, I'm not really that good at typing. Lambda. Apply. So you see there is a function that, as a result, always returns lambda, because that's the only thing we can have in this universe. And as an argument takes what? No surprise, lambda. That's our language. We'll be talking today only about this thing. Okay? And now let's play with that. So we have a public static. We have right now Java world. What can we do with such thing? Okay, let's define some lambda. Identity. It's like takes x, returns x. Okay, what can we do with that? Let's display it on the screen. Identity. Is it really sensible? Who thinks it makes sense? Well, it really doesn't. You will see the result. It's just some, okay, because by the way, system out println is not from this world. It's not really this definition, but okay. We can play a little bit more to see. We take identity and apply identity to itself. Is it sensible? I don't know, probably not, but let's see it. Okay, so you see that, it worked twice, we get the same result. Okay. Before I show you something better, let's talk about more lambdas in mathematical way. So we have identity. Okay, how can we make a step further? One another lambda, who knows? I know you know, but somebody else. Okay, so now very revolutionary idea. We can create this lambda. How does it look? How do we translate it to the human language? It's the lambda that takes an x, you see there, and produces another lambda, another one. Everything after first dot is an expression that it's in fact identity. So we have something that eats one argument and produces identity that we already described. So, by the way, you can look at this as a function from two arguments, because it eats the first one, and then if you have a second thing, then this second thing will be returned. So, to make it, to visualize it, if we do it with we have, for instance, we have borrowed from other universe. In this universe, we have only lambdas, but from other universe, for a moment, we've borrowed a trumpet and a tomato, because they were, cheap. So, we have this lambda and we apply it. There should be a space here to trumpet and tomato. So after applying to trumpet, the first thing, we get this thing inside. So we have lambda from y that returns y, and we have still this application to do with a tomato. So right now we make this application, tomato, and of course with this expression that's identity, we get the tomato. So great, it works.
You should do this with Indian spices.
Okay. Maybe next time, thank you. I knew you have great ideas, okay, thanks. So, and here we have another lambda that takes an x, then returns a lambda that takes y, and still returns x. You see, it's more tricky right now. So if we do it with a trumpet and a tomato, it's like we do it with a trumpet. So it's a trumpet return. So we get a function that takes an y and returns always trumpet. So this tomato, if we apply it, will be ignored and we get a trumpet. And after that, we have, of course, we have to give back the tomato and trumpet to the other universe, and we go further. So, of course, we can create such lambdas that take some lambda x, lambda y, and then as a result, we have to apply to lambda x, y as an argument. That's another possibility. So, as you see, we have an empty universe, but still we can do a lot of plays, of course. So, let's play. That's our play field. So, as you see, I have definition of identity. I hope you see this. Okay, there is a second screen. So, what can I do? Right now, I will do some kind of cheat. I am a wizard, I told you. So, there is a project on the GitHub, because, you know, presenting this thing like this lambda with system out println wouldn't give us any meaningful result. So, I have created a project on the GitHub. By the way, it's open source, so I'm not selling anything. By the way, it's useless, but this project, what it does, it's able to take that lambda and print it nicely on the screen. What is this? Just take a lambda and what is this? By the way, there is a mathematical theorem that says that it's impossible, but still I do it. For me, it's not a problem. Okay, so we take this, this is this smart display and things from this package. So I take this smart display and I will display this identity. So just for you to how it looks like, blah, blah, blah. Like I've displayed this and I'm translating it from the Java word to the something that looks like a mathematical term. Okay, I hope it's easy. So we will play a little bit more. We have this funny lambda, like this. Okay? What it makes? Let's just display it. Okay, so we have this second thing. By the way, I already taught you with a trumpet and tomato how it works. But okay, let's make a step further and write a lambda that's called a true. By the way, it's the same as funny. It's just the same function, the same lambda. And we'll of course display it. Of course, there shouldn't be any crazy, I would say, surprises. It's just like this. I printed it here. So you see, those two things were recognized as the same. By the way, if I write here like, I don't know, A, B, and return A, like this, it should still display what? X, Y, and X, because in this package I don't care how the things are named. I start with X, Y, and just present it. So the names are not important. By the way, in Lambda Calculus it's called alpha transformation. I've already forgot it. Okay. Nevertheless, we can always replace the names of the variables as long as they stay the same. So it's like renaming.
It's called a closure.
Not really. Okay. Okay, well, I just forgot the mathematical term for something. But okay. No worry, it's not about this. So we go further. Because we will define lambda called false. Okay? like this. False. And we'll display it. Oh no, before we display it, I will introduce right now something useful. Another lambda. We have lambda that's not an incident. Why we call them a true and a false? As you see, they are different. Because this one returns identity, this one eats the first argument, then eats the second and returns first. So, and now we create a lambda called end. And it looks like that. Not very nice, I would say. That maths. It's just don't be scared. We'll display it. End looks like that. So, ta-da. So you see that's a true, that's a false lambda, and that's the end. By the way, why it's not written here x and y? Because I used another function web p that means for me start with p. It was just to make it consistent with the thing that you can read on a Wikipedia, by the way. It's all really easily written on a Wikipedia. But okay. So right now, I hope for you it wouldn't be a surprise if I write something like that. Result is end. So I take this end lambda and apply it to false and then to true. And right now, I will display the result. What would that be? You see, that's true, that's false, and that's the result when we apply false and a true, and it's like this, it's false. Great. So, to show you that it really works, I will change this thing here to a true. And what happens? You see? The same. It worked. So, using only these stupid lambdas on an empty universe, okay, in a Java without anything, we've created some basics of Boolean calculus. So, we can go, of course, farther with this. Like, I can introduce right now lambda that's called OR, and I will not waste time to do step by step everything. Let's just see OR false and a true, and of course I can do lambda that it would be called not. Looks like this, and just we can display not false. Okay, so we see how OR works. We'll do OR true and false, and then we'll see what's not false. So true or false makes a true. You see it works. Not false makes a true again. So we've created complete, I would say, Boolean calculus using lambdas. No integers, no Java low-level Boolean, nothing. Only lambdas, only functions. Okay, that's great so far. Let's go further. Because you may say, okay, Boolean calculus, it's very easy. We can go with numbers, because that was the problem. What can we do with numbers? We can start very simply. Like this lambda, magic stopped working, is called 0. So 0, by the way, you know what's 0? You've seen this term before. How have we called it? 0 is something that takes one argument and then returns identities. So it's on the screen before it was called false. So you see the C language made it real. The 0 is false. In our definitions also. So 0 is the same as false. And okay, what is 1? That's just definition. At the moment, I'm not doing any math. I'm just introducing a concept. So that's the concept of 0. By the way, it's only convention. As on the screen before, what's true, what's false, that's a convention. This, which I showed, is the most mainstream one, the most used. So we will see it on the Wikipedia, but that's not the only one. You can introduce some other conventions, some other ways to define what's true or false. Like in the computer language, you can represent Boolean like true or false with -1, 1, whatever. It's the same with lambdas. There are many ways. This way is the most popular one. But it's the same with numbers. There are more ways to define what is number, what is 0, what is 1. but this is the most popular one. So that's a 1. Okay, let's display it, because that would be possibly better. So 1 is something like this. And so so 0 is something that we take an f and then return identity. 1 is something we take an f, then next step we take x and then we apply x to f. That's a 1. Okay? That's something. So that's our definition, and let's go further. What is 2? And that should explain you the way we go. Just, yeah. 0 is like this, 2 already described, so 1 is already described. 2 is like we take an f, we take an x, and we return f twice applied to x. So let's make it like that. A number is a lambda that in fact takes 2 arguments, an f and x, and makes so many applications of f as the number it represents. So if it was 5, we should see here 5 times f. It's like this, just a convention. So, okay, in this moment we can do something really great. We can introduce successor, as we've said. So a lambda that takes some number and makes it 1 number bigger. Of course, we can display this successor, and then we can try it with 1. Yeah? And see if it's the same as 2, and maybe then we try it with 10 and see if it's like this. By the way, here is something crazy. Cardinals from integers. So in this Bedlam project, there is a class called Cardinals where you can transfer from integers in Java to such lambdas and vice versa. So it's like just only utility. But okay, let's display it. So like I am switching between 2 words. So 2 words like this. So 0, 1, 2 you've seen. So successor looks like that. Not very nice, but it works. You see, successor from 1 is like 2. Exactly, it works. Successor from 10 is like how many times? 1, 2, 3, 4, 5, 6, 7, blah, 11 for sure. You can count on your own. By the way, this thing works online on a server, so you can try it on your own, or you can try it using this package. There are tests, and everything should be clear. So let's go further. Plus, because if we have a numbers, a successor, we can introduce a plus operation. It looks like this. It's obviously not very clear, and I don't have time to describe it, but let's see if it works. We can, right now, this A and B, as you see, in order to not write this lambda x, blah, 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 something, I created these things in my package that create a valid lambda that represents 6 or 7, like this. And right now, we will play with that. With A, we just show it, and the plus. The whole plus. As you see, the application is right here. So we take a plus operation and apply to A and to B. And there should be a number. So let's see what would be displayed. At the end, so we have A, it's representing 6, you see, 6. B representing 7, and plus is 1, 2, 3, blah, surely 30. I don't have time to count, but for sure. So, by the way, we can even convert it. So I can convert back again this element to integer using my package. So, okay, it works. You see? So we have plus. We can define multiplication, and okay, just do it. Multiplication from A and B, and we should see the result just at the end. So multiplication from 6 and 7, as you see, was 42. Yeah, great, it works. So you can count all those F's. So you've seen, without nothing in Java, having only this stupid interface for lambda and using only, not using integers, not using booleans, nothing, only application, we've created the numbers and the plus operation and multiplication. And we can, it's not the end. We can go further. We can go to, to this. Because someone may ask, okay, plus and multiplication are easy. What would that be with minus? So let's try it. Maybe we'll just introduce a 9 as a number, and then that's operation called predecessor. So minus minus, as you call it in C++ or Java. So let's see how it looks like and what would be the number before 9. So, sorry, just works or not? Okay, well, at the moment I've only displayed. So it's like 9, and right now I will present what's 9 minus 1. Like this. I'm using this predecessor and with 9. And what's the result? I hope it's not a surprise for you. It's like 1f less. It works! Great! So we have, having a successor, what kind of mathematical operation can we introduce? Come on, it's simply subtraction, yeah? So let's do it. It looks like this. Oh, okay. You know, I won't play with that because that's obvious. You can do it on your own. I will do something more fun because we don't have that much time. So we have subtraction, looks like this. You can later train on your own. Let's do something more crazy. Let's define what an if is. So not a number, not multiplication, just an if, as a thing you use in your languages. So if lambda. What's this? What's an if? Something that takes a condition and does one thing or another. If a condition is true, then we do something, and if it's false, then something else. So if lambda takes a condition C, and then takes something that we call true, so operation that we do if it's true, and then we take something that F, operation we will do as a false. So like 3 things for every if are needed. A condition, what if true, what if false. And those are exactly those 3 things. And how it's defined? Magically like this. And it works. So, of course, as long as condition, this true or false, is something that is consistent, that conforms to this true and false that we defined before. So like, you know, false is something that returns identity, and true is something that returns the first element. So that's the definition. I don't have time to show you that it really works, but we'll use it. So right now we'll introduce operation called is0. So what is is0? Looks like this. So it's something that returns true if the element that we give it is 0, or otherwise it returns false. By the way, this boolean false lambda and boolean true lambda are defined here. So you see that true lambda is simply nothing more or less lambda as defined before. It's just for convenience to not repeat myself every time. So we've defined lambda called is0. Okay, why do I do it? Because I want to show you some really great stuff. Right now, who knows what LEQ stands for? Yeah, great. You know assembly. Oh, great. So, so that's operation. That's called. It will return true if something is less or equal to something else. So, right now I do something very crazy. I call it begin mathematical magical math, because I define a special operator, special lambda called autocall. It's the, I would say, most rude lambda you can think of, because that's autocall, and it takes x and return x applied to x. So it's like, you know, go on, do it to yourself. I don't use it. You know, play with yourself, yeah? That's not very nice lambda, but it works. So we can right now define even more crazy lambda. It's called y. It's very, very known lambda. It's a so magical combinator. Who knows this? Fixed point combinator. Like, it's using this autocall. But okay, I don't have time to explain you what it does. Okay, what it is. But what it does, one great thing, it takes a function and make it recursive. Why do I need that? Because if I want to use, let's pretend I'm doing a factorial. I will show you, who knows what a factorial function, that's very easy is, yeah? Probably who can do it recursive in Java? Great. So it's very easy to do it with recursion. The problem with lambdas, if I use it like that, lambda, so factorial, and then something, and then I would have to call factorial once again. In this moment, what would happen, apply, that compiler would say me, you can try it with Java, that in body of definition of this lambda, I cannot use it. It's different with the functions. Inside of the body of the function, I can refer to this name. But with the variables, right now all our functions are variables, I cannot refer to itself. That's the problem. I cannot do recursion. And there is a solution for that. It's this Y combinator. So, how would it be with Y combinator? We have to prepare something crazy. It almost looks like factorial, almost, because if something is 0, then we'll return 1. You can read, so if 0, then we return 1. Otherwise, what we do? We multiply this n that we get with something smaller by 1. And it's this. Does it compile? Compiles. Okay, so far so good. Compiles. We have some kind of g. By the way, this g has two parameters. N, that's a number, and r, that's crazy thing needed by this Y combinator. So right now let's use this. Factorial is simply Y combinator applied with g. And right now we have, let's define a is something that is a number 3. So we'll display it. And then result, we'll just make a factorial from this 3 and from this number, yeah? And by the way, we'll display it twice using this normal display and converting into the Java integer to see if it works. So we have a number 3, we have factorial function, and you see factorial of 3 is 6. Of course, for you it would be easy. Lake made it serious. Lake made it with, for instance, 6 here. You see it works great. So if you count all those f's, you see that it's 720. It's exactly factorial from 6. And you can be even more crazy. I am more crazy. I will do it with 8. Right now this thing is burning. I hope there is a fire extinguisher somewhere. Oh, as you see, whoa, some great field of f's. Whoa, like this. And if I scroll it down and I'm very, very patient, what will I see? Can you count all of them? Who has counted? Oh, okay, there is a function that counted all of that. And at the end is 40,000. I hope it's a valid result. I haven't counted on my own. Somebody can try it. Okay, so as you've seen, with nothing, with just this interface lambda and a pure function, I've created, right now I would call sophisticated math, a function with recursion. It's really great. You've seen ifs, so what would be the point of this whole play that I did? The point would be that probably everything that you can imagine, that you can compute, that you can program, can be done with this simple language. Who agrees? Yeah, good, good. You should agree. You know why? Because Turing, the guy, said, already and proven in 1937, that in fact Lambda Calculus and Turing machine are equivalent. Lambda Calculus is Turing complete, so everything you can do on a computer, you can do mathematical way with this Lambda Calculus. So you can do calculation on paper without computer. It works. So, great thing, great step. So, right now let's go back to our holy grail. You know what was the point? To make something that will decide if the theorem is valid or not. If we have some, let's say, hypothesis, theorem, if we can automatically make it, say that it's true or false, like Pythagoras, whatever, yeah? So how would that be? Every theorem in mathematical theorem looks like this. If something, then something. So, as you see, if is something we can write with lambda calculus. Statements, of course, and conditions, all of this we can write with lambda calculus. So, if we write it as a lambda expression, like this, maybe we could simply, maybe using another lambda, tell if this thing, at the end, evaluates to the simple true or false, would be great. Because it would make, if it's true at the end, it is equivalent to true, then it means this theorem is true, it's valid. If it would be false, if it would be equal to false, it would be, not valid one. Okay, great thing, but then comes the problem. It doesn't really work like that. It's not that simple. And to show you the why, the best one idea that's in fact used in the theorem why it's not possible is to use this this root lambda called autocall, and then create another lambda called omega that takes autocall and applies autocall to itself. And let's just see what happens if I run this code. Moment, I haven't finished really. Okay, I've finished. You see here stack overflow error, because problem is, there exists such lambdas that you cannot really analyze with another lambdas. Because whatever, those are some kind of bombs. You do something and they explode because they call themselves. And you cannot build in this language some kind of a stop mechanism that would prevent this to happen. So whatever you do, there will be existing such expressions that will bomb your smart solutions. Yeah, like this. And in fact, the church, the creator of Lambda Calculus, proven using such approach that no computable functions, so the things that you can, for instance, do with Lambda Calculus, can decide if this, for instance, is equivalent to true or false. It's not possible. In this moment, it means we don't have easy math. Mathematicians still have things to do. They have still job. By the way, maybe because my church was a mathematician, he didn't want to lose a job. But you see something funny, because if you go to the Stack Overflow, by the way, you've seen Stack Overflow, right now the page Stack Overflow, there is a question. Most efficient way to test equality of lambda expressions. Those guys haven't heard about this theorem, so they just tried and they implemented that. I'm still scared to test it, because it's proven mathematically that it doesn't work, but then they post a solution. How great is that? Okay, you can try on your own if you're not scared. Okay, Stack Overflow has everything. So, there is even more funny problem to that, because generally, so let's conclude this. We've started with a set theory that we've shown that it was not that elegant and consistent, not intuitive as we wanted it to be. So Alonzo Church and other guys tried to introduce a new theory with lambda functions as a fundament building block to make mathematical more consistent, more fun, and maybe to achieve a little bit more. But at the end, they created mathematical. That's really valid mathematical, and a lot of people use it, but it doesn't lead us further. Should I end? No. Okay, I think I have like 10 minutes. Okay, great. So it failed. So they created something useful, something funny, but it doesn't lead to Holy Grail. Why? And there is a problem. So maybe there is something better. We should build a mathematical out of, I don't know. So sets failed, functions failed. What else can we use? Coffee? I don't know. But generally there was a very nasty guy. You've probably heard about him, Kurt Gödel, who just proven that any theory that we build, any, cannot be totally consistent. It means that whatever funny, good theory we build, as long as it's enough to reproduce arithmetics in this theory, so even the basic one, like this. It will contain some theorems, some statements that are really working, are true, but you cannot prove it using this theory. So it's very, I would say, bad news, but there is a theorem, by the way, you can read that, it's not that complicated to understand. In fact, Kurt Gödel shows this statement, that it's true, but you cannot prove it. It's fun. Okay, and yeah, I have still time, so if you have questions, you can ask me in a moment. Just let's sum it up. For you, that's funny thing I shown you, how to do lambda calculus in Java. You can read that in Wikipedia, but it's encrypted with this mathematical language. But as I shown you, it can be easily recreated in Java. I even created for you a package that you can use, or you can do something similar on your own. That's one thing. By the way, this was very, very, I would say, not very deep knowledge. I had only 1 hour, so I skipped a lot of problems, like order of applications. That's probably the bigger. Our lambdas eager, evaluating on lazy. By the way, if I did it with lazy, it would look a little bit not that nice, but it would be more powerful. But I didn't have time to really prepare that. So who knows what a lazy evaluation is? Okay, so just an explanation. If you use languages like Java, C, whatever, those are eager. So if you have a function from some other function as an argument, first this argument is calculated, and then result, like 42, and then you apply to your function. Lazy languages just take it and evaluate it once the moment is needed. For instance, if you take another function that goes to database or whatever, and you never use it in the sign of the body, if you are using lazy evaluation, then you don't call it. So lazy evaluation is sometimes more efficient. Sometimes. So that's one thing. So that's the most important, maybe only thing not useless in this speech. That's the proof that whatever you program, you can surely do it in a pure functional way. Sure. So there is no excuse for you that say, oh, this functional programming, that makes no sense, you can do only simple things. No, I've proven, I've shown you, everything you do it now, you can do with pure functional way. Okay, agree? Yeah, that's proven by Turing. So you should do functional programming from now. At least you don't have to use it every day, because sometimes it's not very efficient, not very even readable, as you've seen. That wasn't readable. But sometimes it really makes sense. Makes things, unbreakable. And yeah, this lambda calculus just funny training there, and some sources. If you go to the Wikipedia on lambda calculus, you will see all those things I've shown you, really one by line. I tried to really follow the Wikipedia to make it easy for you. While doing this, I had some problems. And I found out in this exact moment one guy was doing C# version on a blog, Dixon's blog, and he even went way farther. And so these things are repeated that I shown you today, are really covered deeper in this blog. So I say it helped me really to fight with factorial. So that's the address. I can recommend you one book. This book doesn't really cover lambda calculus much. It's only a little bit. But it's really great book for inspiration. It's Roger Penrose's Emperor's New Mind. You can read there about the Turing machine. You can even see implementation of Turing machine on paper. It's really like a number. It's really great thing. So this guy is crazy. So there is this package I created for you for visualization. It's only used to visualize. In test you can see how to play with lambdas. It's on my GitHub. It's called Bedlam, whatever it means. And the presentation is somewhere. I will post it to Twitter. So right now, if you have some questions, please ask. No questions? Oh, there is a question.
So you said you can do everything in a functional language that you can do on a Turing machine, which from the point of calculability is true. But what happens to computational complexity?
Okay, I cannot really answer your question. That is really like you are are those really more complex calculations that I would do with functional? If that's your question.
No, actually, what happens with the performance?
Oh, it depends. Okay, if we talk about performance, like, you know, functional programming wasn't very popular for years because of the performance. And the biggest problem was memory, in fact. I learned functional programming with SML in the 90s. And really, instantly I've seen that, wow, this thing is great because it takes me like half of an hour to write one line of code. But once it compiles, it always works. I do not need any tests. It works for sure. It does what I wanted. That's the great power of functional programming. At that time, SML or such languages were slowly becoming useful, but not really great. Then came Haskell. But at the moment, Java isn't the case. If you do functional programming with Java, you can read that because of lacking things like tail recursion, it's not very efficient. But the Haskell, for instance, it's quite efficient language. It really depends on what are you doing, because those functional languages, if you don't have mutability, so compiler can do a lot of nasty tricks with lazy evaluation. But it of course depends.
This is actually just performance optimization.
Mm-hmm.
Computational complexity actually takes it to a more abstract level and see how your performance scales.
Okay, so I cannot answer this question. So in fact, that's what you. So computational complexity is like how I cannot really answer this. Hey, any question? Yeah.
Is there any particular kind of problem calculation where this is practically better than some other approach? Consider this is applicable.
Okay, surely for Lambda Calculus itself is more scientific trick, mathematical. But if you are asking about Lambda Calculus or functional programming, pure function. So I would say Lambda Calculus, okay, I'm not really a scientist, I'm not working on that, I'm really normal developer doing, not really funny stuff with WebSphere. So I don't use their Lambda Calculus, but so I cannot really answer that. I would say I don't know any. Okay, I only know that mathematicians use it, really to go farther. But it's right now not very. This branch of mathematics, Lambda Calculus, was like in exact popular before the Second World War in 30s. It was like huge thing, and then after the Turing machine, it's slowed down. And right now, I don't know if there are even new things in this area. People are playing with that, but sorry, I'm not really, as I said, mathematician right now. So. Yeah? Okay, so if there are no more questions, then thank you very much.